When designing a battery system for 5 kV switchgear to switch the coils during utility outages, estimating the load and determining the required battery capacity is vital. Without specific information about the switchgear coils, accurately estimating the load can be challenging, but reasonable assumptions can be made. Switchgear coils typically draw a current between 20 and 40 amps at 5 kV. The number of coils in each section of switchgear is also a factor, and it usually ranges from 1 to 3 coils per section. Let's walk through an example calculation. If we assume a current draw of 25 amps and 2 coils per section, the load per section can be calculated as 2 coils multiplied by 25 amps, which equals 50 amps. The duration for which the batteries need to support the load hinges on the duration of the utility outage, which is generally unknown and can vary widely. Battery capacity measured in amperes is critical. As a general guideline, we can assume a utility outage duration of 8 hours and a desired battery life of 24 hours. For example, assuming a load of 50 amps and a desired battery life of 24 hours, the necessary battery capacity can be calculated by multiplying the load, 50 amps, by the duration 24 hours, which gives us 1200 amp hours. Based on these estimates, a battery system with a capacity of approximately 1200 amp hours would be needed. This system might consist of multiple batteries connected in parallel to achieve the required capacity. It is crucial to verify the load. You should contact the switchgear manufacturer or conduct measurements to verify the actual load of the coils. Following load verification, the next step is to select a battery type and model that meets the required capacity and voltage, which is 5 kV. Finally, the appropriate charger size needs to be calculated based on the battery capacity and the desired charge time. After selecting the battery and charger, adhere to the manufacturer's instructions for battery installation and commissioning. In summary, firstly, estimate the switchgear coil load by considering the current draw per coil and the number of coils per section. Secondly, calculate the battery capacity needed based on the estimated load and the desired battery life during a utility outage. Thirdly, design a battery system, potentially using multiple batteries in parallel to meet the required capacity. Fourthly, verify the actual load by contacting the switchgear manufacturer or conducting measurements. Fifthly, select a battery type and model that meets the capacity and voltage requirement. Sixthly, determine the appropriate charger size based on the battery capacity and desired charge time. Lastly, install and commission the battery system according to the manufacturer's instructions. In the context of switchgear, understanding the intricacies of control power transformers, or CPTs, is beneficial, as they often play a crucial role in powering auxiliary equipment, including the coils. Control power transformers reduce the voltage from the main power source to a level suitable for control circuits and devices. They are designed to provide a stable and reliable power supply, isolating control circuits from the main power system. The sizing of a control power transformer involves calculating the total volt-amp load of all connected devices, including coils, relays, and indicating lights. It is recommended to add a safety margin, typically 20 to 25%, to account for future expansion or unforeseen loads. The volt-amp rating of the CPT should be equal to or greater than the calculated total volt-amp load. Control power transformers are selected based on their volt-amp rating, primary and secondary voltage, and other specific requirements of the application. They should comply with relevant industry standards, such as those set by the National Electrical Manufacturers Association, or NEMA, and the Institute of Electrical and Electronics Engineers, or IEE. Proper installation and maintenance of control power transformers are critical for reliable operation. This includes ensuring proper ventilation, regular inspection of connections and insulation, and periodic testing to verify performance. It is important to protect control power transformers from overloads and short circuits using appropriate protective devices, such as fuses or circuit breakers. In addition to control power transformers, uninterruptible power supplies, or UPS systems, can be used to provide backup power to switchgear control circuits. Uninterruptible power supplies provide continuous power in the event of a power outage, ensuring that critical control functions remain operational. They typically consist of a rectifier, a battery bank, and an inverter. The rectifier converts alternating current power to direct current power to charge the batteries. The batteries store energy and provide power during outages. The inverter converts direct current power back to alternating current power to supply the load. The size of the uninterruptible power supply is determined by the total power requirements of the connected equipment and the desired backup time. Factors such as efficiency, battery type, and operating temperature should be considered when selecting a UPS system. The selection of batteries for switchgear applications is an important consideration, as the battery's characteristics directly impact the reliability and performance of the backup power system. Several battery types are commonly used in switchgear applications, including lead-acid batteries, nickel-cadmium batteries, and lithium-ion batteries. Lead-acid batteries are the most widely used type due to their low cost and high availability. They are available in flooded-in valve-regulated lead-acid, or VRLA, configurations. Flooded lead-acid batteries require regular maintenance, such as watering, to ensure proper operation. Valve-regulated lead-acid batteries are sealed and require less maintenance, but they are more sensitive to temperature variations. Nickel-cadmium batteries offer longer life and wider operating temperature ranges compared to lead-acid batteries. They are more expensive than lead-acid batteries but provide better performance in demanding applications. Lithium-ion batteries are becoming increasingly popular due to their high energy density, long cycle life, and low maintenance requirements. They are lighter and more compact than lead-acid and nickel-cadmium batteries, making them suitable for space-constrained applications. Battery selection should consider factors such as the required capacity, discharge rate, operating temperature, and maintenance requirement. It is important to choose a battery that is designed for the specific application and operating conditions. Battery chargers play a critical role in maintaining the charge of the batteries and ensuring that they are ready to provide backup power when needed. Battery chargers are designed to provide a constant voltage or constant current to the batteries, depending on the battery type and charging requirements. They should be sized appropriately to match the battery capacity and charging characteristics. The charger should also provide protection against overcharging, overdischarging, and short circuits. Proper battery maintenance is essential for ensuring the long-term reliability of the backup power system. Regular inspections should be performed to check for corrosion, damage, and loose connections. Batteries should be cleaned and tightened as needed. Periodic testing should be conducted to verify the battery's capacity and performance. Records of battery maintenance and testing should be maintained to track the battery's condition over time. In addition to the battery system, other components of the switchgear control system, such as relays, contactors, and terminal blocks, should be carefully selected and maintained. Relays are used to control the operation of the switchgear, such as tripping circuit breakers and energizing control circuits. Contactors are used to switch power to various loads, such as motors and lighting. Terminal blocks provide a convenient means of connecting wires and cables. All control system components should be rated for the appropriate voltage and current levels. They should also be protected from environmental factors such as moisture, dust, and vibration. Regular inspections should be performed to check for damage, corrosion, and loose connections. In summary, designing a reliable battery system for switchgear applications requires careful consideration of load estimation, battery selection, charger sizing, and maintenance. By following industry best practices and adhering to manufacturers' recommendations, you can ensure that the battery system provides reliable backup power when needed, enhancing the safety and reliability of the electrical system. When sizing the battery charger, several factors should be considered to ensure that the charger can adequately maintain the battery's charge and provide sufficient current during periods of high demand. These factors include the battery capacity, the charging voltage, the charging current, and the charging time. The battery capacity is the amount of energy that the battery can store, typically measured in amp hours. The charger should be sized to provide enough current to fully charge the battery within a reasonable amount of time. The charging voltage is the voltage at which the charger charges the battery. It should be matched to the battery's voltage requirements to avoid overcharging or undercharging. The charging current is the amount of current that the charger provides to the battery. It should be limited to prevent overheating and damage to the battery. The charging time is the amount of time it takes to fully charge the battery. It depends on the battery capacity, the charging current, and the charging voltage. In general, a faster charging time requires a higher charging current. To calculate the appropriate charger size, you can use the following formula: charger current equals battery capacity divided by charging time. For example, if you have a 100 amp hour battery and you want to charge it in 10 hours, the charger current would be 100 amp hours divided by 10 hours, which equals 10 amps. It is important to note that the charger current should be adjusted based on the battery type and the manufacturer's recommendations. Some batteries require a lower charging current to prevent damage, while others can handle a higher charging current for faster charging. In addition to the charger current, the charger voltage should also be carefully selected. The charger voltage should be matched to the battery's voltage requirements to ensure proper charging. Overcharging can damage the battery and reduce its lifespan, while undercharging can leave the battery with insufficient energy. Most battery chargers have automatic voltage regulation to maintain the correct charging voltage. It is important to verify that the charger voltage is compatible with the battery voltage before connecting the charger. When selecting a battery charger, consider the following features. Firstly, automatic voltage regulation, which maintains the correct charging voltage. Secondly, temperature compensation, which adjusts the charging voltage based on the battery temperature. Thirdly, overcharge protection, which prevents overcharging and damage to the battery. Fourthly, short circuit protection, which protects the charger from short circuits. Fifthly, reverse polarity protection, which protects the charger from reverse polarity connections. Lastly, remote monitoring, which allows you to monitor the charger's performance remotely. Battery installation should be performed by qualified personnel in accordance with the manufacturer's instructions and relevant electrical codes. The installation should include the following steps. Firstly, inspect the battery for damage and verify that it is the correct type and voltage. Secondly, prepare the battery location by ensuring that it is clean, dry, and well ventilated. Thirdly, connect the battery terminals to the charger and the load following the correct polarity. Fourthly, secure the battery to prevent it from moving or falling. Fifthly, test the battery system to verify that it is functioning properly. Sixthly, label the battery and the charger with the appropriate warnings and instructions. Proper commissioning is essential for ensuring the long-term reliability of the battery system. The commissioning process should include the following steps. Firstly, verify that the battery and the charger are properly installed and connected. Secondly, check the battery voltage and the charger settings to ensure that they are correct. Thirdly, perform a battery capacity test to verify that the battery can deliver the required amount of energy. Fourthly, adjust the charger settings as needed to optimize the charging performance. Fifthly, document the commissioning process and maintain records of the battery performance. Regular maintenance is essential for extending the life of the battery and preventing failures. The maintenance program should include the following tasks. Firstly, inspect the battery for damage, corrosion, and leak. Secondly, clean the battery terminals and connections. Thirdly, check the battery voltage and the charger settings. Fourthly, perform a battery capacity test periodically. Fifthly, replace the battery when it reaches the end of its lifespan. Sixthly, keep records of all maintenance activities. In summary, designing a battery system for switchgear applications requires a thorough understanding of the load requirements, battery characteristics, charger sizing, and maintenance practices. By following these guidelines, you can ensure that the battery system provides reliable backup power when needed, enhancing the safety and reliability of the electrical system. Additionally, consulting with experienced electrical engineers and adhering to relevant industry standards can help to optimize the design and performance of the battery system. The National Electrical Code, or NEC, provides guidelines for the installation and maintenance of battery systems in electrical installations. Article 480.1 through 480.4 of the NEC covers the installation of all stationary batteries. This article provides requirements for battery location, ventilation, and protection. The battery location should be clean and dry and provide sufficient access for maintenance. The battery location should be ventilated to prevent the accumulation of flammable gases. The battery should be protected from physical damage and accidental contact. The NEC requires that battery systems be equipped with overcurrent protection. Overcurrent protection devices, such as fuses or circuit breakers, protect the battery system from short circuits and overloads. The size of the overcurrent protection device should be based on the battery capacity and the manufacturer's recommendations. The NEC requires that battery systems be equipped with disconnect means. Disconnect means, such as switches or circuit breakers, allow the battery system to be isolated from the electrical system. The disconnect means should be readily accessible and clearly labeled. The NEC requires that battery systems be installed in accordance with the manufacturer's instructions. The manufacturer's instructions provide detailed information on the installation, operation, and maintenance of the battery system. It is important to follow the manufacturer's instructions to ensure that the battery system is installed correctly and operates safely. The NEC requires that battery systems be inspected and maintained regularly. Regular inspections and maintenance help to ensure that the battery system is operating properly and prevent failures. The inspection and maintenance program should include the following tasks. Firstly, inspect the batteries for damage, corrosion, and leaks. Secondly, clean the battery terminals and connections. Thirdly, check the battery voltage and the charger settings. Fourthly, perform a battery capacity test periodically. Fifthly, replace the batteries when they reach the end of their lifespan. Sixthly, keep records of all inspection and maintenance activities. In addition to the NEC, other industry standards such as those published by the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA, provide guidance on the design, installation, and maintenance of battery systems. It is important to be familiar with these standards and to follow them when working with battery systems. Understanding NEC Table 310.15b16, formerly Table 310.16, is essential for correctly sizing conductors for electrical systems, including those connected to battery systems. This table provides ampacity ratings for insulated conductors rated up to 2000 volts, 60 degrees Celsius through 90 degrees Celsius, not more than 3 conductors in a raceway or cable or earth with direct burial, based on ambient temperature and conductor temperature rating. Ampacity refers to the maximum current, in amps, that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. To use NEC Table 310.15b16 effectively when dealing with battery systems, firstly determine the load current, which is the continuous current that the battery system will supply to the connected equipment. Secondly, select the appropriate conductor insulation type. Common insulation types include DHHN, THHW, and XHHW. The temperature rating of the insulation should be suitable for the ambient temperature and the operating temperature of the conductor. Thirdly, identify the ambient temperature, which is the temperature of the surrounding environment where the conductors are installed. Fourthly, refer to NEC Table 310.15b16 to find the ampacity rating for the selected conductor insulation type, based on the ambient temperature and the conductor temperature rating. Fifthly, apply correction factors if the ambient temperature is higher than the temperature listed in NEC Table 310.15b16. Correction factors are used to reduce the ampacity rating of the conductor to account for the higher ambient temperature. Sixthly, apply adjustment factors if there are more than 3 current-carrying conductors in a raceway or cable. Adjustment factors are used to reduce the ampacity rating of the conductors to account for the increased heat generated by the additional conductors. Seventhly, select a conductor size that has an ampacity rating equal to or greater than the adjusted load current. The conductor size should be large enough to carry the load current without exceeding its temperature rating. Lastly, verify that the selected conductor size meets all other applicable requirements of the NEC, such as voltage drop and overcurrent protection. In addition to NEC Table 310.15b16, other factors should be considered when sizing conductors for battery systems, such as voltage drop, overcurrent protection, and conductor material. Voltage drop refers to the decrease in voltage along the length of the conductor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that voltage drop should not exceed 3% for branch circuits and 5% for feeders. Overcurrent protection is used to protect the conductors from short circuits and overloads. The overcurrent protection device, such as a fuse or circuit breaker, should be sized to protect the smallest conductor in the circuit. Conductor material can affect the ampacity rating of the conductor. Copper conductors have a higher ampacity rating than aluminum conductors for the same size. In summary, sizing conductors for battery systems requires careful consideration of various factors, including load current, ambient temperature, conductor insulation type, correction factors, adjustment factors, voltage drop, overcurrent protection, and conductor material. By following the guidelines in the NEC and other industry standards, you can ensure that the conductors are properly sized to carry the load current safely and reliably.